Good afternoon. I'm Zakonov. I'm a director of engineering with the Google Kubernetes Engine team.
Hey, good afternoon, everybody. My name is Brandon Royal. I'm a product manager also on the Google Kubernetes Engine team, and we're really excited to be here.
Yeah. So during the developer keynote today, we showed how easy it is to build GenAI-powered applications on a Google Cloud. As part of this session, we're actually going to focus on a practical best practices, tips on how to get from your test environment into production fast, and what you need to be aware. What the architectural best practices, what are the customer best practices to really get you to that production stage. So first, large language models, they bring a lot of power in being able to reason about your data. They come with a few core fundamental problems that needs to be solved to have a successful production workload. First, all the models trained on the public data. It means that they have zero access to your private corporate data. You can fine-tune the models. To truly get quality out of fine-tuning, you need to have a lot of samples. In many cases, you're just not going to have enough volume in your corporate data for proper fine-tuning. So that's first major issue. Second major issue is hallucination. So for some consumer scenarios, hallucination is acceptable. For many production enterprise scenarios, hallucination is a bar that you just cannot afford. So hallucination gets worse as you get into domain specific. And my assumption is that as you work on specific use cases that you need to apply, hallucination is a major thing that needs to be addressed. And third, and probably the most important, when you get response from your large language model, is actually being able to validate that response and anchor back in your own data. What's kind of the source of truth for the response that you're getting. So standard pattern that emerged in the industry to address those three major problems is Retrieval-Augmented Generation, or RAG. So that's pretty much became a default design pattern for all GenAI applications in the last, let's say, 18 to 12 months. Let's talk about, first of all, the pattern itself and why it became so popular. Pattern is very simple. We extended the system with the retrieval system, and instead of sending requests directly to LLM, first we send it to a retrieval system. We extract your corporate data based on a semantic search that's applicable for that request. Second, we enhance the request with your corporate data, and we send combined prompt to LLM. LLM summarizes response, and that response goes back to user. So let's talk about those three problems that we highlighted at the beginning and how RAG pattern helps to address that. First, we still use LLM, but we're not using LLM to purely generate the answer. LLM is used as a summarization engine. And when LLM is being used as a summarization engine, the probability of hallucination drastically goes down. Second, since the answer is anchored in your corporate data, you have a traceability to source of truth. So even in case of the slight hallucination that you may get, you have an extra validation point with the user being able to see the actual source of truth in your corporate data. And that's a simple method to bring your corporate knowledge into LLM system without doing any fine-tuning on the model. So you can do it on a much small amount of corporate data. Across Google, we have a wide variety of solutions, starting from a Vertex, Dataproc, VMs, and Kubernetes. In this session, we'll focus on Kubernetes Engine, and we'll focus on OSS tool ecosystem around Kubernetes Engine. So our HuggingFace integration, LangChain integration, reintegration, and so on, and best practices for building LLM-based applications based on open source tools. One of the key things for this talk is actually anchor everything that we'll be presenting here in the actual experience for both our external customers plus for experience of internal Google teams, as we built a Gemini-based experience for Google products inside Google Cloud. And RAG application pattern is one of the primary patterns that we use inside the Google as well to power our systems. So, 3 key topics that we'll cover as part of the speech. First, we'll talk about best practices for RAG applications. We'll talk about practical lessons. And we'll finish the session with a quick demo that shows you how to start your journey kind of in a streamlined way. Going slightly deeper on the architecture. So as we're looking on the architecture of RAG-based applications, there are 2 major subsystems that you need to care. Your embedding subsystem and your serving subsystem. Those 2 subsystems operate differently and will scale independently and will be optimized independently. For your embedding subsystem, the core elements is obviously your vector database. And there is a set of proprietary databases as well as open source databases for your vector databases, your embedding service, as well as your data processing pipeline and your data stores. So for your embedding system, you need to scale it based on your data processing volume, based on the amount of the data. For your serving subsystem, it has a different scaling requirements. It will scale based on the volume of requests. It will scale based on the patterns of requests. And the key things to consider in your serving subsystem is what you're doing for safety filters. Once more, with LLMs, there is extra layer of security, extra layer of privacy that you need to take care of, as well as your choice of inference server. You may choose a fully managed inference server with Vertex. You may choose to use 1P models like Gemini or run your own models, like, for example, Llama directly on Kubernetes or Mistral or Gemma. So what are the core things to consider when you're developing? First, similar to your traditional microservice applications, loosely coupled design is extremely important. Why? With your traditional applications, before you get to production, before you get to optimal architecture, you're probably looking on tens, maybe 50 iterations. With RAG-based applications, you should expect to go through hundreds, sometimes thousands of iterations before you get to a fine-tuned architecture. Next, OSS, leveraging OSS frameworks, the area is evolving extremely fast. So basing your development on the OSS framework just gives you a lot of flexibility, both from a choice of tools and ability to influence. So once more, we are in a super early phase, expect a lot of churn in the next couple of years in the space as the industry stabilizes across a set of solutions. So bet on OSS is one of the safest bets that you can make at that phase. Retrieval system, the best practices that we see inside the Google, that is not just semantic retrieval based on the vector databases, but really you need to combine it with the relational and document retrieval systems to get best results out of your RAG-based applications. And last 2 is more around kind of classical platform architecture, really making sure that you separate platform concerns from application concerns. And you really design for security and safety at all layers, starting from your platform layer all the way to your application layer. And as I mentioned before, models bring that extra layer of privacy and security that you need to deal with. Now, why Kubernetes and how Kubernetes fits the picture? So a few things. First of all, key reason why we see customers picking GKE, Google Kubernetes Engine, because for many customers, Google Kubernetes Engine is their standard platform for developing their web and stateful applications. And expanding that into LLM-based applications, inference and training, you can reuse all the best practices. You can reuse all the corporate policies that you already have encoded in your Kubernetes platform. Second, with LLM-based applications, you need TPUs, GPUs, and in general, those applications are extremely compute intensive. Price for TPUs and GPUs high, so making sure that you can optimize utilization across all your fleet. GKE platform gives you that end-to-end visibility and optimization for your TPUs, GPUs, CPUs. So that's a foundational layer of provisioning and auto-scaling. On top of that, as part of Kubernetes team, we invest into training as well as in inference, supporting all standard frameworks for training and inference. And we invest in a rich ecosystem support, including Ray, Jupyter, Kubeflow, Spark, and so on, and LangChain that you can bring for the fast integration. And with that, let me introduce Steven to talk about how GE Appliances uses us.
Great, thank you, Alex. Well, as it says, my name is Steven Allen. I am a cloud engineer at GE Appliances, where my team is focused on the development and operationalization of consumer-facing generative AI applications. And today, what we're going to touch on here is Smart HQ Assistant. And so, to take a step back to about a year ago to Google Next 23, GE Appliances announced the MVP release of Smart HQ Assistant, which is a containerized RAG application that utilizes mixed retrieval systems, including semantic and document retrieval, in order to provide a chatbot-like experience for our users to find answers about their connected appliances and about use and care manuals and whatnot. And so at GEA, we're committed to this idea of zeroing the distance between us and the consumer, and Smart HQ Assistant has certainly provided the window to allow us to better understand them so that we can deliver more relevant value to them at a more accelerated pace. And so as I mentioned earlier, this was absolutely an MVP when we released it. And so through our continued partnership with Google Cloud, we've been able to continue to iteratively improve this experience so that we can, improve this personalized experience for our consumers. And so I'll touch on a couple of the optimization strategies that we've employed over the past few months. At MVP release, we followed what is, typically found as this naive RAG pattern. So there's some prompt coming in, there's the retrieval step, the inference step, and then the output. What we've migrated more towards is this advanced RAG system where we have pre-retrieval and post-retrieval steps, and that's where prompt intent classification comes into play. And so one of the first things that we noticed through our usage trends was that our users were interacting with this application more so like a search engine. And so we were seeing 2, maybe 3 words in the prompt, rather than a more semantically significant sentence or full question that you may expect from a chatbot. And then secondly, we noticed that there were broad yet consistent categories in the prompts that we were seeing from users. And so taking both of those inputs, we inserted a fine-tuned foundational model in order to classify incoming prompts so that we could then direct queries within our application for potential query expansion, query routing, and a number of other things in order to optimize the retrieval step here. Secondly, enterprise adoption. It sounds like a broad subject there, but our team is a firm believer that the accuracy and the effectiveness of a RAG system is a function of the quality and the accuracy of the underlying enterprise data. And in order to enable an experience where business users have a direct window into what assistant, in this case, knows or a RAG application knows, we've developed a self-service portal so that our business users can go in, update, test, and then actively deploy changes to our underlying knowledge base without any involvement from our development team so that we can remain focused on some of the more important feature enhancements for the system. And then lastly, continuous evaluation. As I mentioned earlier, we had no idea how users were going to interact with this originally, but through observing usage trends, we've invested heavily in our ability to automate the evaluation jobs that we're running through a set of ground truths and identifying potential degradations and application performance issues as we move forward with additional releases. And so with all of that being said, some of the results that we've seen here is that since MVP release, we've seen a 200% increase in engagements from our Smart HQ users, which is certainly something exciting. But from the development standpoint, what we're more excited about is that 103% increase in answer found rate, which is our KPI for this being a RAG system. And then through our ability with prompt intent classification to handle query routing and additional modularity within our code base, we've been able to reduce the experience latency by 42%. So I'll close with just a couple of keynotes here. meaning from the product side, Smart HQ Assistant has really provided us a better line of sight into the voice of our consumers. And as we zero the distance between, a consumer's problem and delivering value through product increments, Assistant has been an amazing tool for us that we're going to continue to invest in alongside our partners at Google. And then continuous improvement from the engineering side. As I mentioned, this was an MVP. We didn't necessarily know how users were going to interact with the application, but through high levels of observability and continuous evaluation in the platform, we've been able to iteratively develop and deliver improvements so that we can ultimately be a long-term success in production. And so with that, I'll pass it back over to Brandon, but thank you all.
Excellent. Thank you, Stephen, and thank you for the continued partnership. In working with customers like GE Appliance and many other customers across the industry, we've found a consistent set of feedback, a consistent message, and that is 2024 is really the year in which customers are moving from prototype really to production. So we're seeing all of these sort of interesting edge cases and best practices emerge, and really that's what we wanted to focus the rest of the talk on. How can we provide sort of technical best practices from the customers that we work with to help you, our customers, deploy RAG applications? We've also heard consistently from customers that, and hopefully this is clear from what you've heard from both the earlier speakers, that the value of data is really key. And we've heard customers say clearly that they need to provide, or they need the level of control around how that data is indexed, how that data is ultimately queried, how that data is surfaced to the large language model. So a lot of the architectural best practices that you'll sort of see as well are really surrounding around control that you can have of your data. So we're going to focus on a lot of scenarios that we also hear from customers where AI-based products are a core part of their business. So like you heard from Stephen earlier about how their product is really helping their user experience, we're seeing a lot of customers really lean in on building these AI applications that are becoming the center part of their business in the way in which they interact with customers. Now, before we get into the architectural bits, I want to call out an elephant in the room here, and it might be a little awkward, but I'll admit the technology is actually really one of the easiest parts. And that was a consistent piece of feedback we heard from customers, both internal customers to Google as well as customers that we work with. The technology is getting easier and easier to use. It's working with the people in the process. So we really wanted to start, before we get into the technology, I'm a technologist, I love talking about technology, but we really want to focus on what are some of the learnings from the people and process side of the business as well. So the first point that we've heard is really work with legal, work with PR, work with comms. These are going to be ultimately your champions as you build out these applications. We know lawyers love uncertainty, of course, right? So when you think about an undeterministic system where you don't know exactly what your output's going to be, you don't know exactly how your users are going to interact with that system, we need to think about just whole new paradigms of how we manage risk. Right? And that could ultimately change the shape and the scope of your deployment. So engage them as early on as possible. We heard that over and over again. Second, users are not skilled prompt engineers, and they may never be, and that's okay. So let's think about how we actually build that into our systems. Let's build templates that we can use. Let's build pre-processing like Stephen talked about. If a user puts in just a couple of tokens, a couple of words, we need to augment that in meaningful ways so we can get the semantic results back from the system. So think about that early. Third is engage subject matter experts in your data. The data is so valuable. In order to get the retrieval results back or to get the retrieval performance that you're looking for, you need to ensure that that data is chunked and tagged and structured in a way that the retrieval system will get the best results. So work with those subject matter experts who know your data best to ensure that you have the right chunking and retrieval strategy. And then fourth is, we understand testing is hard. And this is, again, a whole new paradigm when we think about testing. But don't just say, you know what, this is difficult to test with unit tests or other integration tests that I'm used to, so I'm going to do manual testing. That is not good enough. So you need to think about what are some of the more automated testing strategies and tools that you can use. And that's a talk in and of itself, but just sort of bear that in mind that you really want to think about automated testing. OK. So we're going to now get into the technology. I'm just going to repeat again what Alex talked about earlier. We're going to break this down into these two pieces. So we're going to talk about the embedding subsystem and then the serving subsystem. And again, these are two sort of separate systems in the way in which they work, but they share a lot of the same technology and patterns. And so we can reuse a lot of the things both between these two subsystems as well as a lot of our existing deployments that we have for traditional applications. So let's dive into it. Now, first of all, implementing on GKE and using things like Cloud SQL for vector databases, this really allows you to have sort of a central set of technologies. You'll notice that GKE is sort of right in the middle of this particular reference architecture, and that's because it serves quite well both on the embedding subsystem as well as the serving subsystem. And that's really because Kubernetes can be used for things like real-time requests, which obviously it's quite good at from an application perspective, but also job-based queuing for your embeddings and your indexing of your vector databases. So you can sort of centralize a lot of your core infrastructure around some of these decisions, and that's ultimately going to help you with that efficiency. Now, let's actually break this down. I realize that was a bit of an eye chart. So we're going to actually take this sort of piece by piece and sort of share some of the best architectural best practices for these different sections. And so we're going to first start with the embedding subsystem. So in the embedding subsystem, what are some of the core components and what are some of the best practices? So again, a lot of customers that we work with need that level of control. They need to control exactly how their data is indexed, how it's embedded, how it's decorated. So GKE and Cloud SQL together can, in a lot of cases, give that level of control that customers ultimately need. Now, in GKE, we have a feature called GCS Fuse, and that's sort of the idea of being able to take data that is structured or unstructured data, excuse me, that you might store in something like cloud storage and actually directly integrate it into your GKE cluster. And that's ultimately going to help with efficiency of reads. GCS v2 is also introducing new caching capabilities, so you can more efficiently read that information directly into GKE. But it doesn't always have to come from cloud storage. Of course, you can read from BigQuery, you can read from FileStore, you can read from a whole bunch of different sources, both within GCP or anything that's connected over a secure VPC. Now, that's sort of the data side. Now, Ray, we heard Alex talk about Ray a little bit earlier. Ray is becoming an increasingly popular choice for data scientists who are building all kinds of AI-based applications, not just for retrieval-augmented generation, but for serving, for training, for fine-tuning. Ray is becoming really, really popular. And that's primarily because it has a core distributed compute and data system that just works really well for AI-based use cases. And so for retrieval-augmented generation, we've seen a really good adoption for a lot of cases like sharding the data. So if you have a large data set, you want to shard that data across multiple nodes, and then you want to use distributed compute in order to do the actual indexing itself. So we can use Ray essentially on GKE on the same infrastructure in order to run those jobs. And then last is the vector database. And this is actually becoming a pretty easy part of the equation now. So many vector database options are out there, including a ton of vector database options directly within GCP, including Cloud SQL and AlloyDB. All right. So when we actually talk about the Ray piece, just coming back to that for a quick second, the scaling characteristics are quite interesting. So when we talk about sharding of this data and actually processing of this data, we also need to think in terms of what is the horizontal scaling and efficiency that we might get. So in some of the testing that we've done internally, we've actually found that not only can you shard that data across multiple nodes with something like Ray, which is going to handle that quite well, right? Because each chunk is going to be independently processed. It's going to use embeddings. It's going to do the vector indexing, and then we'll pass that back as a vector or series of vectors. But we also found that introducing additional GPUs offers near linear scaling for efficiency. So if you're looking for sort of the best approach for processing your data, you can also add additional GPUs, and you can get some great scaling characteristics out of that. Again, GKE is going to sort of provide the uniform compute substrate to do a lot of that work as well. OK. So let's switch gears and talk a little bit about the serving subsystem. Now, from my perspective, I come also from a history of development and application architecture. So this is, to me, where things get really interesting. This is actually where we can leverage a broader part of the open source ecosystem, like LangChain, like HuggingFace, and we can build the components together in order to serve the needs of our users. This is where, again, that loosely coupled architecture that Alex talked about is going to be really important, because ultimately we're going to start with any request that comes in through our front end, and then we can work with various services, either within multiple containers or a single container, in order to route our requests to the appropriate systems. So on the LangChain part, so just for those of you not familiar with LangChain, LangChain is a hugely popular open source framework for AI orchestration. Now, I don't know how you measure the popularity or the success of an open source project, but in terms of GitHub stars, they're doing quite well. The LangChain team should be incredibly proud of the work that they've done in the ecosystem with something on the order of 70,000 GitHub stars and 2,000 contributors, which is significant. And we love Kubernetes. We contribute significantly to the Kubernetes ecosystem. And if you even compare the two, we can see exactly how the LangChain adoption has been trending. So really promising if you're looking for an open source tool that's going to provide broad support across multiple sources for retrieval, for large language models, for first-party systems, for third-party systems, LangChain is really a great choice for you. Now, LangChain also is something that we're investing in, so we want to make sure that LangChain is the best choice for customers within Google Cloud. And one of the ways in which we're doing that is offering support across all of our major databases. So you can do vector database via Cloud SQL and AlloyDB, so that's going to be directly supported within LangChain. But also if you have normal retrieval type use cases of structured data, say that's also supported, as well as nice abstractions for things like chat history. So we want to actually maintain some memory for our chat-based interfaces, and we can actually store all that memory in SQL databases like Cloud SQL as well as AlloyDB with that LangChain integration. So really cool stuff. But we can also, of course, work with LangChain on the LLM portion as well. And hopefully that's pretty obvious to everyone here. We can leverage things like VLLM integrations, text generation inference integrations, and many more. So the front end, ultimately, that's where a lot of the magic happens. But of course, we need to secure this front end in a meaningful way. And Alex mentioned this as well. There are new security considerations when we think about security and risk considerations that we need to think about with RAG-based systems and large language models. So how can we start to address some of those risks and some of those concerns from a security perspective? So we'll go into that here next. Now, let's talk about the data itself. So we talked a lot about data and the value of this data. Data sensitivity is critically important, and we need to think about this not only in terms of how we do real-time data protection, both on the serving system and the embedding system, but also how we actually manage the sensitivity of that data, how we assess the harmfulness of a request and handle that response accordingly. So with Google, in Google Cloud, actually, you can leverage a lot of the same APIs that we use for systems like Context Center AI, Workspace, and a number of others that actually do a lot of this stuff already. They already protect data using these APIs, and as Google Cloud customers, you have access to that. With things like sensitive data protection, you can actually inject filtering, essentially, as a process in your data preparation. And if you think about that for a second, so you're taking all of this very sensitive enterprise data, you're indexing it within your vector databases. You need to ensure that that data, you're not exposing private information or sensitive information to other customers who might query against that database. So sensitive data protection is just a simple API that you can use, I think, roughly 150 different types. That's all sort of out of the box, simple API you can use to filter out all kinds of information. We'll show you what that looks like here shortly. Now, safety is more than just filtering out individual terms as well. So we also need to understand the risk of a particular request or a response coming from the large language model. And we need to have an intermediary which assesses that risk and gives you as developers the decision of, hey, is this something that I accept or reject within my user interface? And that's where Cloud Natural Language API comes in with out-of-the-box features for just that. So just to give you a sense of what that looks like in a demo, we'll show you what that is. So really quickly here, we've got API, or we got our interface where we're first going to look at a scenario of doing some filtering. So we have a prompt, we have a response that has a name in it. We want to filter that out. So we're going to add our sensitive data protection. We're going to point to a name template, and you can see the request and the response. The response is going to have that name filtered. So Robert De Niro is now filtered out. And same thing, instead of a name template, we're going to use a date template. Again, there's a bunch of different templates that we can use. So we make the request, we get the response back. In real time, we can filter out and manage that data. Now, a different scenario that I mentioned before is sort of the sentiment of the request, like what is the potential harmfulness of the request and the response, and how do we build systems around that using the natural language API. So we're going to, again, add that filter there. We're going to ask a question that might be perceived as harmful. And so we're going to sort of set a filter range of what is sort of appropriate that we think for this response. And we can see we ask the same response back, or sorry, same question back, wait for our response. And I think momentarily it will tell us, yeah, OK, so this is not something we can display. Right? Again, and as developers, you have that choice of sort of figuring out where the appropriate line is for that API to do text moderation. So that's how that works on the harm reduction as well as data sensitivity. Switching gears a little bit. Oh, sorry. Yeah, there we go. Now we can go to the next one. Switching gears a little bit, we also want to recognize the security around the boundary of our application is equally important. So sensitive data protection is going to help with sort of data sensitivity and protection between individual systems. But now we need to think about the boundary of our application, how we ensure we control access to that system using Google native tools. So this is where things like identity-aware proxy come in. And identity-aware proxy, for those of you not familiar with it, essentially provides an ability to control access using IAM to your system. So it'll actually directly integrate into load balancers. So if you're using load balancers natively within the GKE API, you can do that. And then for RAG-based systems as well, you can control the front end of your chat-based interface, all of your APIs, and any of the systems that your customers might use. So what this might look like. So we can easily enable IAP. So really easy, we just turn it on for our particular service. And what this is going to do is actually going to do a whole lot of magic behind the scenes. This looks super simple, but what we're actually doing is we are enabling IAP for that particular service and authenticating through the front-end load balancer. So we'll go to the load balancer, see that configuration. We'll load that up really quickly, and we can see we don't have access. This user doesn't have access, as we'd sort of expect. Now, in order to re-enable that, we'll go use standard IAM permissions. So if you've got IAM for all of your other services, which you would within GCP, you can use that same paradigm to secure all of your front end. So I'm going to add that principal, the same user request. We'll add them in here. There's a specific role for a web user. We can save that here. And then we'll make that same request to the front end once that policy is updated. And we should get our 200. And that's going to secure access both of the web front end as well as the API backend behind that. That should work. I know that because it's a video. All right. So that's pretty simple, right? IAP is a hugely powerful tool. I did not do that justice. Again, could be a talk in and of itself. But super sophisticated controls around things like geofencing, if you have certificate-based requirements, if you have very hardened security controls where you need to be very specific about exactly which users get access to your RAG-based systems, IAP is a great solution for you. OK. The last question we get from a lot of customers that are new to building RAG-based applications on things like GKE is, hey, I have the AI/ML expertise, I have the app development expertise, but I may not necessarily have all the expertise within Kubernetes. How do I have a more sort of fully managed experience within Kubernetes, given the control that I ultimately need, while also getting access to the accelerators, things like GPUs and TPUs that I ultimately need? GKE Autopilot is a mode of operation within GKE that gives you a sort of serverless-like experience while having full access to the Kubernetes API. So we actually manage the nodes underneath. We provide a pod-level SLA. So our SREs essentially are responsible for the uptime of those components within your RAG-based application, ultimately then saving customers operational toil for managing the infrastructure itself. And again, we can provide direct support for the accelerators. So you can use GPUs, you can use TPUs, whatever you need, or GPUs currently. So we want to make this easy to consume, right? So we went over a lot of different components and different parts and practices. How do you actually make this real? If you're going and deploying an application, how do you actually get started? And so the team has actually been working really hard on providing some quick start solutions with sample applications that you can go and reference, You can deploy them from a Terraform-based template or directly through the UI. And it's going to integrate all of the pieces that I just showed you. And so you can actually see what a real live best practices reference deployment will look like on Google Kubernetes Engine with all of the other services pre-integrated. And this is, again, going to leverage HuggingFace for the models themselves. So we're pulling down a Mistral 7 model on text generation inference. It's going to use LangChain for all of the integrations into the databases, Ray for the distribution of the data indexing. And so if you don't believe me, I'm going to show you. And I'm going to actually show you this live here. But my computer went to sleep, so give me a second. All right. So hopefully everyone can see that. OK. So we're just going to start within GKE. So as of this week, if you go to your overview page for those GKE users out there, if you go to the overview page, you'll notice some new options that are here. So these are our quick start solutions. So we've heard loud and clear from customers, we want opinionated ways of deploying various application patterns. And so some really common ones in ML are RAG, like we talked about today, but also deploying more generic Ray-based platforms, as well as Jupyter. So we wanted to provide some quick starts to make that easy to deploy. So we've got our RAG on GKE Quick Start. We're going to view the details here. And we'll launch that. And all it's going to do is just ask for some very basic information around our deployment. Give it a name, give it a service account ID, basic description. There's some other configurations if we want to use things like identity-aware proxy that I showed you earlier. There's some additional configuration steps there. But generally speaking, this is pretty easy. And we specify our cluster, have it create a new cluster, and it takes just 20 minutes or so to deploy. We're not going to wait 20 minutes, I promise. I do have this already deployed, so I can show you what it looks like. But it's going to deploy all the major components in a GKE cluster. Now, one of the things that it's also going to deploy is Jupyter. Now, there's lots of different ways of doing model training and sort of interactive data science with Jupyter. We, in the reference architecture, deploy Jupyter Hub. There's lots of different ways of doing it. I'm actually directly connected to Jupyter Hub via my local IDE, so I can actually show you what the Ray portion of the embeddings actually looks like using that reference architecture. So if you imagine for a second, we've got a data set. Right? So our particular scenario, we've got a whole bunch of movies, right? It's not enterprise data, sorry, it's the data that's openly available in the reference architecture, so bear with us. But we've got a movie data set, we want to pull it down, we want to chunk that data, and we want to use Ray as a distributed compute system to actually vector index all of that data and upload it to Cloud SQL. So we're going to go through that really quickly. All right, so we'll generate our embeddings here. So there's a bunch of other steps I'm going to skip here, just sort of getting this ready to go. Hopefully this is all connected. OK, cool. All right, so got our embedding step. We're going to make our connection directly to Ray. So we're just essentially exposing our Ray head node here so we can make that connection. We are already connected. And this is actually where we're going to start to do our data parsing. So we've got our data set, and what we're going to do is we're going to chunk it out into various pieces and then parse it using our Ray flat map. And so that's basically going to say, hey, I'm going to shard now this data across all of my Ray head nodes in order to process this. So we'll run that there. And now the really cool part. So all of this is actually happening on my, it's actually remotely connected to my kernel, but it's not actually doing any work on the remote workers. So what I want to do is use the Ray API in order to actually distribute that task, distribute the task that I've set up to actually shard or actually process my data. So I'm going to use this Ray remote decorator and a little function for processing the data. And you can see what it's going to do. It's going to go through, it's going to use that mapping interface, and it's going to go through each and every one of my chunks. So if I've got a handful of workers, it's going to distribute across a handful of workers. If I've got hundreds of workers, it's going to distribute that across hundreds of workers. So you can imagine the power and flexibility that you get. This is all managed with GKE. So just like a normal application, you would set up your node pools and all your resources and deploy Ray on top. Now, we won't go through the whole process here of watching this go, but ultimately, we're going to now get back all of our vectors that we can then load back into MySQL. And when that's all done, that's going to look something like this in an end application. So that's going to be available in Cloud SQL. Now I can actually do queries from my front end against that. So let's see what this looks like. I got to remember the prompt I'm going to use here because I don't remember it off the top of my head. Okay, oh, that's right. I was going to ask about Las Vegas. Okay, so I'm pretty tired. I'm going to go figure out what kind of movies I want to stream. And again, a movie data set. So I want to figure out what movies I want to stream on my way back from Las Vegas. All right. Not to ask the system what it does. And really what it's doing behind the scenes is it's going and asking my vector database. It's grounding the response in that data, and then it's summarizing that response with the LLM using Mistral. So got a good response back. Lighthearted movie. Perfect. That sounds really good. I'm not really sure what that, oh, yeah, Kentucky Fried Movie. I'm not really sure what that is, but hey, we'll give it a shot. Okay, awesome. So that's it. So that's how you build a RAG-based application. Went through a whole lot. We do want to, just switching back to the slides here. So we really do want to hear from you. We are working hard to make sure that we're providing the best product, the best tools, the best capabilities for you to build RAG-based and AI-based applications in GCP. So we really want to hear from you. If you scan that QR code, it's going to ask you a few questions about some of the use cases that you're currently using, but it also gives you an opportunity to connect with us, the engineering team, the product team, the experts in the field that help to support you. So if you wouldn't mind taking a few minutes to fill that out, that'd be wonderful. We appreciate it. And then feedback is a gift, so we appreciate any additional feedback you can provide on the session itself.